Hello everyone. My name is Naitik and I'm a rising junior at Freedom High School in Chantilly, Virginia. I'm incredibly honored to be speaking at the Global Health Leaders Conference this year. I'll be presenting on how artificial intelligence is helping us discover new small molecules that can target neuroinflammation, which is a key mechanism driving Parkinson's disease. A little bit about me. I'm a student researcher at Georgetown University, where I work on AI-driven approaches for drug discovery in neurodegenerative diseases. I've competed at the International Science and Engineering Fair in Columbus, Ohio. I lead my school's biology Olympiad Club, and I volunteer with VOSEP. My long-term interests lie at the intersection of neuroscience, bioinformatics, and biomedical AI. Parkinson's disease, or PD, is the second most common neurodegenerative disorder worldwide, affecting over 10 million people. As you can see in the figure, the burden is rapidly increasing. We're expecting 17 million cases by 2040. The disease hits low-income and aging populations hardest. PD leads to loss of dopaminergic neurons in a region called the substantia nigra. These neurons produce dopamine, a neurotransmitter essential for motor functions. However, when these cells die, patients experience tremors, rigidity, and eventually cognitive decline. And while we still have drugs like levodopa to relieve symptoms, we still don't have a therapy that actually slows down this dangerous disease. So, what causes Parkinson's in the first place? It's like a puzzle with many interconnected pieces. On this slide, you can see 6 major biological contributors. About 10 to 15% of these cases are due to genetic mutations like LRRK2, PINK1, or SNCA. Other factors can include pesticide exposure, head trauma, and heavy metals. Inside neurons, we see oxidative stress and mitochondrial damage. There's also abnormal alpha-synuclein protein aggregation, which forms Lewy bodies, as shown in this image. And finally, emerging research also points to a disrupted gut-brain axis, where harmful protein may start in the digestive system and travel to the brain via the vagus nerve. But perhaps the most intriguing mechanism and the focus of my talk is neuroinflammation. So, in the brain, microglia are the immune cells that act like first responders. When they detect stress, such as alpha-synuclein buildup, they release inflammatory signals like TNF-alpha and IL-1 beta. You can see how these molecules trigger a cascade that damages nearby neurons, creates more inflammation, and promotes alpha-synuclein aggregation. This is like a vicious feedback loop. At the core of this loop is the NLRP3 inflammasome, the blue structure highlighted at the bottom. It acts like a control panel. Once activated, it recruits caspase-1 and triggers pyroptosis, which is a form of programmed inflammatory cell death. However, overactivation of NLRP3 has been directly linked to PD progression in both patient and animal samples. So, how do we really stop neuroinflammation? Well, we can use small molecules, drug compounds that are low in molecular weight and can penetrate the blood-brain barrier, otherwise known as BBB, as shown in this visual, as a filter between the blood and the brain. Small molecules are ideal because they're orally bioavailable, meaning that we can usually take them as pills. They're chemically stable due to their favorable ADME profiles, and they're effective for chronic conditions. One promising molecule is MCC950, which inhibits the knock domain of NLRP3, which prevents it from oligomerizing. Below that, you'll see other examples like BAY117082 and OLT1177. Each works on slightly different mechanisms but aims to reduce inflammation at the main source. However, the key challenging is finding new molecules that are even more effective, and that's where AI comes in. Imagine trying to find a useful Lego brick in a pile the size of the galaxy. That's how hard traditional drug discovery really is. The number of possible drug-like molecules is over 10 to the power of 60, which is more than the atoms in the universe. Instead of screening millions of molecules in lab, we now use artificial intelligence to predict which ones will actually work. AI-based drug discovery can either be structure-based or ligand-based. Structure-based discovery often involves taking structures of a protein target in a compound to accurately predict how well a compound binds to its corresponding target, mainly using molecular docking simulations. Ligand-based discovery handles numerical data using QSAR models to analyze thousands of known molecules and learn which features like molecular weight, polarity, or shape can be important in predicting IC50 values. AI-based approaches can also predict pharmacokinetics, which are ADME profiles, or even toxicity. The figure on the top left shows the difference between traditional and computational drug discovery pipelines, highlighting that structure-based and machine learning-based approaches significantly reduce times and costs associated with drug discovery. The flowchart on the right displays a common pipeline of target identification, hit identification, or virtual screening, lead optimization to improve on lead compounds, preclinical testing of compounds in the wet lab, and eventually clinical trials. And this image also shows how molecular docking perform to predict binding affinities. Let's look at a real success story. DSP-1181 was the first AI-designed CNS drug to enter human clinical trials. It targets the 5-HT1A receptor, which is involved in Parkinson's-related depression. In the process here, AI was used to generate new molecules using generative models, optimize them with reinforcement learning, and finally, screen for ADMET properties, which stands for absorption, distribution, metabolism, excretion, and toxicity. Instead of screening 2,500 compounds, they only needed 350, and the whole process took under 12 months. That's a revolutionary shift. Parkinson's disease is rising globally, and we still lack therapies that target the root causes. Neuroinflammation, once seen as a symptom, is now a validated therapeutic target. And now with the power of AI and small molecule design, we can build faster, smarter, and more precise pipelines to treat PD and beyond. Thank you so much for listening. I'd love to connect and continue the conversation. Additionally, here are my references which I use to create this presentation. And I would like to thank my mentor at Georgetown University for really inspiring me and supporting my research in this discipline. I would also like to acknowledge the GHLC team in organizing this conference and providing an opportunity for me to speak here. And lastly, I would like to thank you for watching this video. Thank you for listening to my video. And if you would like to contact me, here is my email and my LinkedIn. Thank you.